Buenas tardes a todos. Es un gusto verlos aquí hoy. Ya tenemos en este momento a 104, 105 participantes, así que vamos a empezar la presentación del webinar de hoy. Con este webinar tenemos el placer de seguir la serie de webinars 2021 de la Comisión de Exploración y Desarrollo del IAPG. Esta serie de webinars se desarrolla casi todos los jueves a las 16 horas. Se compone de 5 ciclos. El primero es Últimos descubrimientos exploratorios en la Argentina. El segundo, Magmatismo y sistemas petroleros. Exploración offshore en el Atlántico Sur, que es este ciclo. Microsísmica y exploración de reservorios shale de la Argentina. El tema de estos webinars es compartir experiencias y ampliar miradas. Y con ellos buscamos crear un canal que permita la difusión y el intercambio de conocimiento con un enfoque multidisciplinario. Hoy continuamos con la segunda sesión del ciclo Exploración Offshore en el Atlántico Sur. Estamos Sebastián Galeazzi y yo, Néstor Valianti, compartiendo la conducción del ciclo también, Joseph Bernaus y Alberto Sánchez López, como coordinadores de la sección de preguntas y respuestas, además técnicos y asistentes del IAPG. Este ciclo se compone de 9 sesiones de webinars que se extenderán a lo largo del año. Nuestro foco es la exploración offshore en el margen sudamericano del Atlántico Sur, al sur de la dorsal de Walvis, Río Grande. Así que mismo tocaremos aspectos del margen conjugado africano que ayudan a la comprensión del margen sudamericano. Las exposiciones cubrirán temas como geología prerruptura de Gondwana, el rifting regional mesozoico, ruptura continental de Gondwanas y rocas madres en la región, tema de hoy y de la sección de mayo, la evolución mesozoica, cenozoicas y sistemas petroleros de las cuencas más prospectivas de la región. También abordaremos temas de estudios de oceanografía y ambiente, y aspectos de infraestructuras, operaciones y regulatorios asociados a la actividad offshore en la Argentina. Antes de empezar, queremos agradecer a los oradores, al IAPG, a la Comisión de Exploración y Desarrollo, liderada por Claudia Borbolla, por el esfuerzo y el soporte material y técnico para hacer realidad esta serie de webinars. Buenas tardes, Sebastián. Te doy la palabra para que puedas presentarnos a los expositores de hoy. Adelante.
Hola, Néstor. Muchas gracias. Muy buenas tardes a todos. Hoy tendremos 2 exposiciones de 25 minutos cada una. Las 2 serán en inglés. La primera exposición tiene por título Rifting Mesozoico del sudoeste del Gondwana, la precuela de la apertura del Atlántico Sur en el Cretácico temprano. Mesozoic Rifting of Southwest Gondwana, a prequel for the early Cretaceous opening of the South Atlantic Ocean. Y esta es una presentación que va a dar el doctor Juan Pablo Lovecchio de IPF. La segunda exposición tiene por título Formación, Imagen y Perforación Científica en márgenes de rifts volcánicos en el Atlántico noreste y sur. Formation, Imaging and Scientific Drilling of Northeast and South Atlantic Volcanic Rifted Margins. Será presentada por el profesor Sverre Planke de VBPR y University of Oslo. Por favor, recuerden que deben escribir sus preguntas al final en el panel de P&R, preguntas y respuestas. Pueden hacerlo en castellano o en inglés y en cualquier momento durante las presentaciones. Please remember that you can write your questions in the Q&A panel at any time during the presentation. Vamos a hacer una sesión conjunta de preguntas y respuestas al final de ambas presentaciones. So will be a joint Q&A session at the end of both presentations. Entonces, permítanme entonces tener el gusto de presentarles al primer orador, Juan Pablo Lovecchio, es geólogo de exploración senior en YPF, obtuvo un título de geología de la Universidad Nacional de Córdoba, en Argentina, en 2009, licenciatura, una maestría en geociencias de petróleo en el IFP, Institut Français de Pétrole, en Francia, en 2011, y un doble doctorado en la Universidad de Sorbona y la Universidad de Buenos Aires en 2018. Ha trabajado en exploración de frontera en diferentes países de América del Sur y África durante más de 12 años. Actualmente se desempeña como secretario y tesorero regional de la AAPG para América Latina y el Caribe y es presidente de la AAGGP para el periodo 2020-2022. Juan Pablo, es un placer tenerte con nosotros hoy. Te cedo entonces la palabra. Por favor, activa tu micrófono y comenzá a proyectar tu presentación.
Bueno, muchas gracias, Sebastián, Néstor. Agradezco al IAPG por la invitación y arrancamos con la presentación. Ahí estamos. Bueno, como dijo Sebastián, lo voy a hacer en inglés porque tenemos a Sverre y a público internacional para que nos entendamos todos. So today I will present the results of my PhD thesis and some updates on that. I will be talking about the Mesozoic rifting of Southwest Gondwana and how this was a prequel for the early Cretaceous opening of the South Atlantic. So how this, so that we can understand together how the history behind the geology of the supercontinent of Gondwana influenced the opening and the architecture of the South Atlantic passive margins later. So where does this come from? The idea was to discuss this prequel thing, and it came from the idea of how we look at the present day and how important it is to look at the story, the history, and the evolution to understand what we have today and why it is like that. So I wanted to bring an example on that, and this is very common now with these series and films to have prequels of different characters, superheroes or villains like in this case. So we have Darth Vader, and this Star Wars saga is famous from the 70s and 80s. And we all know Darth Vader, this character that said, "Luke, I'm your father." It's the super villain from Star Wars. And what can we learn from this kind of sagas? The idea came to me when I realized that the films that George Lucas did later in the 90s and 2000 were actually the story of this little boy that grew up and became Darth Vader. And he wanted to explain in this saga, in these films from 1999 and 2002, how this Anakin Skywalker became Darth Vader. So the idea is to highlight how important it is to understand what happened before to better comprehend how it worked and why we have what we got. So our Darth Vader here would be the South Atlantic, and we know that's this ocean that separates America from Europe and Africa, open very diachronically and in different stages. And this is our present day figure, let's say. But where does it come from? How did it become what it is? The South Atlantic, the Atlantic Ocean and the South Atlantic in our case. But obviously we need to look back at least to the Permian, to the Paleozoic, and actually much further into the deep time, into the Proterozoic, and how the different cratonic blocks amalgamated, forming the supercontinent of Gondwana, and how their structural grain produced fabrics that have been inherited and have conditioned the rifting processes and the development of structures such as the normal faults that form the centers in our extensional basins. So we will look into detail today at the especially we had some insights into the Paleozoic history with the presentation from Victor last month, Victor Ramos. Today we will look at the Mesozoic rifting history and the influence on that, on the opening of the South Atlantic Ocean in the early Cretaceous. So how do we break these supercontinents? We break them through rifting, and rifting can be triggered with different processes. The most common is, the easiest to understand is the influence of plumes or heat anomalies that obviously produced uplift and extension on the crust. Anomalies are what produce, let's say, the active upwelling of the asthenosphere, and this is why we call active rifting to the rifting that is triggered through this mechanism. Another way of producing rifting is with orogenic gravitational collapse, when cordillera or an orogenic building grows up to a point where it's not stable anymore. It can collapse extensionally and thus produce rifting. And finally, and possibly the most common process, and yet not so well understood in some parts of the world, is the process of passive rifting, which in this case, the upwelling of the asthenosphere is the asthenosphere passively ascends, and the rifting here is produced by the horizontal stress pulling apart the crust. What we want to say when we say horizontal stresses, what we mean is influenced by plate boundaries or action, and in this case triggered by subduction, as is the case of the South Atlantic opening in the early Cretaceous. So successful rifting leads to breakup, you know that, or oppositely, unsuccessful rifting leads to aborted rifts or abandoned rifts that are very common on the continental crust. But let's look at the successful cases. You know, you have extension, so a stress regime that produces separation of blocks and thus creates accommodation space. You have rifting, you have normal faults, you have the centers, and eventually with the thinning of the crust and the onset of oceanic crust accretion, you develop a passive margin, and you have what we call continental breakup, and the eventual transgression of the sea and a marine oceanic basin, with the development of passive margins on both sides of the continental plates that bound that oceanic basin. And then, you know, later on, those continents drift apart and this ocean expands. When it comes to types of passive margins, there are three end members. The magma poor passive margins, or hyperextended, are the ones where you extend the crust like a very very plastic ductile crust that breaks apart, but the lithospheric mantle continues to resist, so you don't have this huge outburst of asthenosphere that is present in these magma-rich margins. Magma-rich margin is the case of our South Atlantic, where we have a more brittle crust that breaks apart, and this the interaction with magmatic processes produces, at the time of breakup, the development of these wedges in the continent-ocean transition zone that are called SDRs, because they are formed by seaward dipping reflectors, and they are normally tholeiitic basalts interbedded with continental sediments or shallow marine sediments, and they in place during breakup, and this is what Sverre will tell us more about in the next presentation. And the other end member is the transform margins, where strike-slip movements dominate between tectonic blocks. Our case here in the South Atlantic is the magma-rich or volcanic margin. And again, we're looking at this supercontinent perspective, the Wilson cycle, where you have an orogen, you rift it, you break up, you open an oceanic basin, then they drift until they become unstable and subduction initiates, and then you have another orogen and eventually a continental collision, and this cycle restarts. Today we will be looking at this part of the cycle, how we start from an orogen and end up throughout different tectonic, different rifting stages into the breakup of the South Atlantic. This is not the only case, and for multi-stage rifting and the influence of this inheritance in the fabric of the basement. For example, here, the Northeast Atlantic, that is one of the cases that Sverre will mention later, has also been conditioned by, as you can see here in green, this Caledonian deformation associated to the Caledonian orogeny in the middle Paleozoic or in the Silurian Devonian, and also the Variscan orogeny in the late Paleozoic. So obviously these orogenic events in the Paleozoic had an influence and and produced some inheritance that was profited then by the different Mesozoic rifting events and eventually the Cenozoic breakup, or the Cenozoic rifting event that led to breakup or was successful. Today we will be looking at the South Atlantic, and in the case of the South Atlantic, the scenario is somehow similar. We have older orogenic events. This part of southwest Gondwana is an amalgamation of cratons of different age, but mostly Paleoproterozoic, that were amalgamated in the Neoproterozoic during the Brasiliano Pan-African orogeny. Here you see some of these mobile belts and the age of their deformation, so they are mostly restricted to the Neoproterozoic. That's one how occurred this amalgamation of blocks in southwest Gondwana of cratons. And then the margin was an active margin throughout the Paleozoic with accretion of different terrains on the southwest margin, in the Cambrian, in the Ordovician, in the Devonian, and so on. And the last one of them was the accretion of the Patagonia terrain in the south that produced volcanic arc, but also the development of the fold and thrust belt in the Ventania region in onshore Argentina, and its extension into Africa in what is known as the Cape Fold Belt in South Africa. How did this supercontinent start to break apart? We need to look at this picture. It's from where Gondwana was at the end of the Permian, as part of the supercontinent of Pangaea, and the continent started to drift to the northeast with a polar rotation here in northern South America. And this drift produced extension in the retroarc of South America, as has been illustrated here by Ryle. What we did in this study was to summarize the chronology of the different rifting events in South America and Africa, and to put together a model to understand how the whole system worked and how the different rifting events ended up with the opening of the South Atlantic. So here we see a map of the Mesozoic basins of southern South America, in this case, especially Argentina and the offshore basins. And in this chart to the right, I have summarized the age of rifting, with active rifting marked here by the black bars, and in gray sedimentation of triggered by other or associated to subsidence triggered by other processes. So active rifting is what we are interested in now, and it's what marking here in black. So if you look at in the big picture, you can group some basins that formed through rifting in the Triassic, and then you can group basins that were active during the Jurassic, and finally in the Cretaceous, with particularly here detailed the opening, the diachronous opening of the South Atlantic Ocean that's becoming younger towards the north, right? I think I will move to the laser point. And we will look at this particularly looking at two examples that I studied in my thesis: the Colorado Basin in northern offshore Argentina, in south of the Buenos Aires province, and in the Malvinas Basin in the south. In the Colorado Basin, and something that I like to point out here is that you will see this kind of QR codes. You can use your camera in the cell phone to access the papers, to download the PDF of the papers if you scan them, and they will be present in different slides related to the different publications. So here in the Colorado Basin, we are looking at two seismic transects. We have an east-west here at the bottom, and largely speaking, north-south here at the top. And here we are seeing both the Colorado and Salado basins. What we interpreted here in the Colorado Basin in particular is the development of at least 3 rifting stages. We knew that this orthogonal, the fact that the Colorado Basin and the Salado are orthogonal to the margin was possibly associated to a previous rifting event. What we have found here is that previous rifting event that is marked here in blue actually intersected older faults that were associated to an initial rifting event that we associated to the Triassic. So what we saw is that these red faults that are here colored in red form tilted blocks. Especially here we are looking at the northern flank of the Colorado Basin, and in these tilted blocks there's Permian preserved, which is that pre-rift with parallelly bedded horizons shown here, and we see that those faults have a detachment level here between 10 and 15 kilometers of depth, and that detachment is intersected by this normal fault that's forming the main depocenter of the eastern Colorado Basin. Here, this eastern Colorado depocenter, sorry, which is bounded by this northward dipping normal fault that we can see here. These blue faults would be the second associated to the second rifting event. And we see that they not only transect them in the north-south perspective, but also in the east-west. We have some small depositors associated to the first rifting event that are intersected by this second generation of faults. And finally, the third rifting stage in this case is the one that is clearly associated with the breakup of the South Atlantic, and is related to these green faults that are more parallel oriented with respect to the continent ocean transition and the SDR wedges that we can see here mapped in purple. And we see that these Cretaceous faults, or these faults associated to the South Atlantic Rift and thus early Cretaceous, are restricted to a 200-kilometer wide stripe along the continent-ocean transition zone. And here again, we are looking at the seismic section south of the Salado Basin, where we see these deposenters formed by normal faults deepening towards the continent, as the faults bounding the inner SDRs also have this characteristically deepening towards the continent. Our interpretations for the Colorado Basin come from the seismic, so we don't have really direct geochronological ages to tie those rifting events to time. What we used to do that was the thermochronological evolution of the onshore outcrops of the Ventania and Claromeco Basin that show cooling ages that are restricted to the Triassic and Jurassic. And these cooling ages, we interpret them as formed during the exhumation of the basin border or the footwall during rifting. This is an indirect way of getting an age for the rifting of the Colorado Basin, and we see that most of the exhumation of this Ventania and Claromeco region is bounded or is limited in the Jurassic, in the Triassic and Jurassic, and this area was fossilized, to put it in a way, later. So we are not really looking at exhumation ages of Cretaceous ages that could be associated with the South Atlantic opening. Another thing that we see here in Colorado is that these faults that we had interpreted in red, that are the first generation of faults, seem to be the extensional reactivation of the former of the offshore extension, let's say, of the Ventania fold and thrust belt. You see that we see a deepening of the detachment level that we associate to this fold and thrust belt of the northern limit of Patagonia that was extensionally reactivated in this stage in the Triassic. The compressive deformation is of Permian age, and it was extensionally reactivated in the Triassic, as we interpret from the thermochronological data. So that's an example in the north. What we did in the south, in the Malvinas Basin, is a slightly different tectonic setting. We do have an extensional basin, and we did seismic interpretation, and in the position close to here in the Rio Chico High is one of the boundaries of the Malvinas Island, between the Rio Chico High and the Malvinas Islands, Malvinas Basin, sorry. So on the Rio Chico High, we had access to samples from a well, and what we did is to date with the treacle zircon the rocks that are forming the seam rift, within the seam rift. So within the early seam rift, we did get this Triassic age from a volcanic breccia, this sample M06, and from the top of the seam rift is just the top of the Tobifera series below the Spring Hill Formation in the Calamar Well. We obtained a very nice volcanic age of 169, so Bathonian, Middle Jurassic for the Tobifera in that region. But we did find this, for the first time in the area, this Triassic age, and it's interesting to see that the earliest rifting in this Malvinas Basin was Triassic. This graph summarizes the tectonic evolution of the basin, where we have this in red, these two new ages, and some other ages for rifting in the Cuenca Austral, in the Austral Basin, the Rocas Verdes Back Arc Basin, that show a diachronous rift initiation towards the subduction zone, or towards the trench, let's say, that started in the Triassic and became younger towards the west, and eventually produced the opening of the back arc basin with oceanic crust accretion that are now ophiolites in in the Rocas Verdes Basin in the late Jurassic. So how does this all look in a regional perspective? If we see what we did in South America, and this is a similar summarized chart, summary chart for what we have from Africa, we can group the different rifting events for the Triassic, Jurassic, and Cretaceous, and look at them on the paleogeography and how they were at the time of formation. So in the Triassic, we have a scenario without active subduction marked by this volcanic arc in Chile, with retroarc extension observed in the Bermejo, Cuyana, and the Triassic deposenters of the Precuyano cycle in Neuquén. Also the Central Patagonian batholith, and the extensional basins in the Deseado Massif and this new age from Malvinas. We have another group of deposenters, in this case formed by intracontinental rift in Africa, what we call the Karoo-1 rifting event, and the extension into South America in the Santa Maria deposenter of the Paraná Basin in Brazil. And the other important aspect of the Triassic is the extensional reactivation of the fold and thrust belt of the Ventani Cape system that we have a negative inversion, and so what we call formed extensional deposenters bounded by listric faults, which were before thrusts of the late Paleozoic orogen. In the early Jurassic, what happens, the most important thing that happens in southwest Gondwana is the impingement of the Karoo plume here in South and in Eastern Africa, with the development of different fault-bounded deposenters filled with continental sediments and volcanic rocks that are very well dated and with ages restricted between 184 to 180 million years. And we interpret this 2,000-kilometer radius of action, of activity for the Karoo large igneous province that would bring a limit in this position of the purple circle. When we look at the South America, we have the development of the Salado and Colorado basins, and also the Neuquén basin here. We interpret we put here the early Jurassic Precuyano deposenters that are also elongated along the northern boundary of Patagonia. And you see that they are oriented more or less parallel to the deposenters in Africa. So we interpret that they are of the same age, but out of the influence of the magmatic plume. And finally, in the retroarc, we had the development of the Chennai magmatic province. In this case, it's mostly retroarc with the subduction-related chemistry for the volcanic rocks. You know, the Chennai is a largely silicic province, and there is a diachrony here also towards the south and the west, and a very large diffusion of magmatic rocks, and in the Cañadón Asfalto, in the San Jorge, and obviously the Malvinas and Austral Basin with the formation of the Tobífera series. So we have two sections here.
You have 5 minutes, Juan, left, please.
Yes, we have two sections here. The one here showing the Chonnaique in the south and the extension in the Malvinas Plateau, and another one here in northern Patagonia showing these retroarc deposenters in the Chubut and Cañadón Asfalto, and in a very distal position, the Karoo deposenters in Africa. In the late Jurassic, we have the formation of the Oceaniqua and the Rawson Valdez deposenters, and extension in the Malvinas Plateau, and eventually the extension in the Malvinas Basin and in the southern part of Patagonia produced the oceanic crust in the Rocas Verdes Basin, Pacac Basin, as shown here. What's interesting here, and this is a zoom of that map and for the late Cretaceous, is how this late Jurassic rift triggered the opening of the South Atlantic. Here we have the position of the rifting between the Agulhas Malvinas and the future reach of the South Atlantic. And we think that this this opening occurred in the Cretaceous, we think associated with the rotation of the regional stress field. We compare it with what's happening in the Gulf of Aden, in between Arabia and Africa, and where we have also preceding oblique rifting that is migrating towards the Afar plume and finally open the Red Sea in between Arabia and Africa. And I wanted to include in this presentation these very new results from a magnetic data acquisition performed in the Malvinas Plateau, which shows these lineations that are interpreted as magnetic anomalies, and that you can see that go very well with the interpretation of structures that we had here for the late Jurassic, and with the structural grain for the reconstruction that we presented in this paper last year. And what's interesting here that we will update on our models is the extension of oceanic crust within the Malvinas Plateau that will need to be included especially regarding the geometry of the ridges. So finally, we have this late Jurassic rifting that gave birth to the South Atlantic throughout the process of a rotation of the stress regime. There must have been a fabric that favored the strike-slip movement along the Agulhas Malvinas fracture zone, and we have a less volcanic southern segment and a more volcanic margin north of the Colorado fracture zone in association with the Paraná, Tendeca, Lip, and the Tristan plume. This is published, so you can see the publication for more details. To conclude, what I wanted to show is how this the geology of the supercontinent of Gondwana influenced with the varying stress regimes, and how the old structures were reactivated at different times, as for example in the Triassic with reactivation of old terrain sutures in southwest Gondwana, in the Jurassic with the Karoo plume and the extension in the southwest associated to the margin, and finally in the Cretaceous with the opening of the South Atlantic and the strike-slip reactivation of the Agulhas Malvinas fracture zone. What's key here is that this South Atlantic started in the core of the Gondwanite orogen, an area that was subjected to different tectonic and extensional events in the Triassic, in the Jurassic, particularly in the late Jurassic with oblique rifting. And so this area is key to understand why the South Atlantic opened there since the Valanginian. So that's the key message here, is that the rifting was a very complex process that occurred in several episodes throughout the Mesozoic, and the South Atlantic opening was only the end stage for that rifting. The Colorado and Salado and Malvinas Basin formed with the Triassic and Jurassic events before the rifting, before the South Atlantic opening. And in the late Jurassic, this area between the Rawson, Valdez, and Oteniqua basins formed a Bermuda's triangle that we can call, that was the core of the Gondwanite orogen, and is the area where let's say the seed where the South Atlantic Ocean originated from. So that's what I wanted to tell you today. Thank you very much.
Wonderful. Thank you, Juan Pablo. An excellent presentation. So please stay connected and remember that we're going to have these sessions, the Q&A session at the end of the second presentation. So thank you very much, Juan Pablo. The next presentation is by Professor Sverre Planke. The title of the presentation is Formation, Imaging, and Scientific Drilling of Northeast and South Atlantic Volcanic Rifted Margins. Sverre Planke is the CEO of Volcanic Basin Petroleum Research, VBPR, and part-time professor in the Center for Earth Evolution and Dynamics in the University of Oslo. He is a geoscientist with research focus on the processes and structure of volcanic rifted margins and volcanic basins based on integrated geological, geophysical, and theoretical methods. Sverre is a co-founder of VBPR since 1999 and P-Cable 3D Seismic since 2007, and holds a bachelor's in science in geological engineer 1985 and a master's in science in geophysics in 1987, both from the University of Utah, and a PhD in geology in 1993 from the University of Oslo. Sverre has co-published more than 125 papers and 5 patents with a Google Scholar H index of 51 and over 10,000 citations. So please, Sverre, it's a pleasure to have you here with us today. Please connect your microphone and start sharing your presentation. The floor is yours. Thank you.
Well, thank you very much. I hope you see my presentation and can hear me clearly.
I hear you very well.
Very, very good. Yeah, so I'll just start with a beautiful picture from Kamchatka, subduction-related magmatism. Some years ago, it was in about 5 years ago, they had a big eruption in fissure eruption that was captured by this image. So we've been doing field work here to look at this large basaltic flood field. It's about almost 1 cubic kilometer of basaltic lava that was erupted during this time. And you can also see the mountains here in the background, like Klitschevskoye is erupting at the same time. So it's one of the more active volcanic provinces in the world. And this is here mainly for the beauty, but also showing some of the type of processes that we are interested in. So I will follow on from what Juan's been talking about. I'll initially say something on volcanic rifted margins, just some terminology and overview and the structure. Then I'll move into the Northeast Atlantic to look at what we've been doing in terms of seismic interpretation of volcanic flow fields and silts and vent complexes, and then moving on towards the South Atlantic with the breakup magmatism and seismic interpretations, and then some synthesis and conclusions with touching onto breakup models and prospectivity and scientific drilling plans. And this pictures here sort of encompasses the sort of integrations and the world that we are working on. So this is the seismic horizon. Here we see vesicular basalts where all the vesicles are filled with oil, and this is from Western Greenland, and from Iceland here, the Hularound eruption some 10 years ago. So basically what we volcanic or magma-rich passive margins, as Juan nicely introduced, are volcanic-rich margins, and they're dominant in the world. Some people will say something like 75 to 80% of the continental margins are magma-rich, whereas we also have these magma-poor margins, particularly in Iberia and Newfoundland, but also some of the Central Atlantic rifted margins are magma-poor. And then we have these sort of unspecified that are partly magma-rich margins that we also find a lot in the world. So just took a cartoon here, modified from Hans-Jørgen Kjøll, but just showing the sort of schematically the crustal structure of magma-poor and magma-rich margins. And as you know, then they can have many names. So if it's magma-starved, non-volcanic rifted margins, non-volcanic rifts, or hyperextended and exhumed margins. So basically you have a proximal margin with fairly thick continental crust, rifted, fault blocked. And then the distal margin, we have extremely thin continental crust, and in some places you will have exhumed mantle rocks, peridotites coming up to the seabed before we move into the seafloor spreading stage, when we generate fairly normal but typically thin oceanic crust. In contrast, a volcanic or magma-rich margin has a fairly thick crust near the continent-ocean transition, and that is due to the addition of melt during the breakup process. So these are typically characterized as seaward dipping reflectors. They can be up to 6 kilometers thick. In addition, we commonly have this high velocity body with P-wave velocities of more than 7 kilometers per second. So typically 7 to 7.5 kilometers per second. That's sometimes termed magmatic underplating. That is basically melt that was ponded near the base of the crust during the breakup process. So it's you have a thickening of this crust both above and below due to the magmatic activity, and then it leads on to seafloor spreading, where we create initially sometimes a thickened oceanic crust before we go towards normal thickness of the oceanic crust. If you look at some data from volcanic margins, so these are two velocity profile, crustal velocity profiles from the Norwegian margin here on the right and the Argentine margin on the left. We can see that the crustal or architecture is quite similar, that we have this typical high velocity body with P-wave velocities of 7 kilometers per second. Here is up to 7 kilometers thick. And we also have this quite similar, strikingly similar crustal velocity profiles on the Argentine margin with again something like 5, 6, 7 kilometer thick high velocity bodies near the base of the crust. And here we have the moho then. Yeah. So this is a cartoon that we've been putting together, which basically shows in a schematic way what we think these volcanic rifted margins looks like, partly based on the Northeast Atlantic. So we have large Cretaceous basins, commonly intruded with sills. Near the tip of these sills, we often find this pipe structure. We call them hydrothermal vent complexes. So they're formed by sort of eruption of hot fluids. Then we have the extrusive deposits that we divide into these outer high, inner seaward dipping reflectors, landward flows, and the lava deltas, and then finally the inner flows that have distinct seismic phases. Below the volcanic, seismic imaging is much more difficult. Reflection data are not so good quality, so this is more of a schematic interpretation. We have often this very well-defined T reflection. Below it, we have a lower crustal body that consists basically of a combination of a continental crust, and we have these ultramafic lenses and also more gabbroic lenses. And when we move towards the continent-ocean transition, we see evidence of well-defined dike swarms. But these type of volcanic margins are often submerged during the Wilson cycle, and field observations, in particular of the lower crustal structure here, are not very common. But we have some fantastic exposures in the Scandinavian caldonides. So this 300-400 meter high cliff sits in the Sarek National Park in Sweden, and basically shows in white here, these are sedimentary rocks. And you can see the layering, and it's cross-cut by two sets of dikes. And we have a student that's been working extensively on this region to characterize the dike complexes and so on. And basically they're formed by about 50% of extension. And we see that the two distinct orientations of dikes, no sills, and they're mutually cross-cutting, so they're formed at the same time. This would typically be some lower crustal type of analog to the to the continent-ocean transition that we find in offshore domains. Lower crustal bodies are even more difficult to define, but we have a region in northern Norway that's called the Seiland volcanic province. It's about the same age, so it's about 600 million years old, where we find these ultramafic rocks cut by more gabbroic dikes. And this we think is also the lower crustal component, so a large-scale magma chamber in below a large igneous province related to continental breakup. So these sort of dikes here would be pyroxenites, very ultramafic, and then they're cross-cutting this layered gabbroic complex. So this could be an example of perhaps what these LCBs actually look like in nature. So this sits up here in Seiland in northern Norway. Okay, so let's move back to the northeast and northwest Atlantic. So we call this piece of ocean between Greenland and Norway, UK for the northeast Atlantic. Between Greenland and Canada, we call the northwest Atlantic. These were basically formed by continental breakup at about 62 to 54 million years ago. And we mapped out in quite some detail the distributions of the different type of volcanic seismic facies units. So you can see here the classical seaward dipping reflectors in the purple colors. And then we see these very prominent escarpments. And then we have the inner flows and large basin provinces that's been intruded by silts. And this is basically our main study area where we have a fantastic database and available for detailed studies. So this is just showing an oblique view of the Norwegian continental margins. We have the North Sea, large number of wells and petroleum field here. Mainly it's the Jurassic. We also have in the mid-Norway quite an extensive petroleum province. Whereas when we move into the Cretaceous basins, we have much less wells, and we also have quite a lot of volcanics when we move towards the oceanic domain. This is the west of Shetland area where we find a very similar geology. Over the last 2-3 years, there have been acquired very large 3D surveys. So this AMN 17 and 18, 19 and 20 by TGS. We've been doing seabed sampling, and we've been doing some high resolution P cable acquisition in this part. And we're also going to talk about this very famous borehole here. This is the ocean drilling program borehole 642. So basically, if you look at the outer margin, this is some seismic reflection data. So it shows SDR sequences here. So they're basically 3 different sequences. We also have this characteristic outer high, moves towards the lava delta and then into the Cretaceous basin. And you see underneath this marginal high, we have quite a bit of image problems. So we have developed different interpretational methods to interpret the breakup complexes. We use the concept of seismic volcanostratigraphy, a subset of seismic stratigraphy, on 2D data. So we map out seismic facies units. Then for 3D data, we use the concept of igneous seismic geomorphology. So again, it's a subset of seismic geomorphology or just normal geomorphology. And of course, well ties and field analogs are very important for us to try to understand these igneous deposits, as there are few boreholes and these are often located in very remote settings. I'll just show you an example of how we do the seismic igneous seismic geomorphology. So I'm zooming into this outer high region. We see the top basalt surface here. It's being strongly faulted in small rift grabens during the breakup process. But if we do the amplitude extraction of the top basalt horizon, we can see that we have very nice flow lows. So the margins of lava flows, we can see pitted surfaces, and we can see compressional ridges. So we're basically looking at here an ancient volcanic terrain that's being subsequently downfaulted. We can do this type of geomorphology also on the west of Shetland area. So here we see the Alen volcano. It's a big caldera here, and this is being cut incised by some drainage systems. So very similar to fluvial channels that you see on Hawaii, or erosional channels. You see some small vents here on Iceland. We can find very much the same in the 3D seismic data and lava flow fields. Perhaps these cones here that is common in some volcanic terrains where you have the eruption here, the lava is streaming out. We see basically exactly the same type of geomorphologies on the 3D seismic data. So here we have the eruption center. It's about 1 kilometer across, and then the lava has been flowing up, and it's imaged here by these high amplitudes that's related to the eruptions. One of the more spectacular images here is made by Edwin Groth at Equinor on the Vøring marginal high. So again, it's a top basalt surface where it's mixing coherency data and RMS amplitude on the top basalt horizon. And again, we can see this sort of lava flows that is streaming from the west towards the east. When it hits the paleo coastline at the escarpment, you fragment and you form hyaloclastites. And these will be transported down the kilometer-high escarpment and be deposited as debris flows on the paleo ocean floor. It's not much to see on the 2D profiles, but as you can see, the igneous seismic geomorphology is really a powerful tool to understand this type of provinces. If you go further landward, we have mapped out numerous of these hydrothermal vent complexes. So they typically here, these sort of crater-shaped features at the paleo seafloor. It can be some kilometers across. Typically they're 1 to 2 kilometers, but they can be up to 10 kilometers. And they're characterized then by infill of sediments that's onlapping on the edges, inward dipping reflections towards a conduit. And these conduits is almost always ending up near the tip of high amplitude reflections that we interpret as sill intrusions. So it's a close association with these vent structures and the sills. And we go and look at this infinity sill in this part here. So it's a seismic data. You can see nicely the high amplitude reflection. It's a sill, mainly layer parallel, but it also got some transgressive segments. Near the termination, we see these vent complexes coming up. So again, here you will see the sort of, you have some steps on the sills suggesting a propagation direction in this way. And then it's sort of the upper part here is just more circular features with very well-defined transgressive features. Yeah. And if you go to the paleo surface, we see that we have just on the depth map, we will have well-defined sort of circular vent complexes. So these are craters at the paleo seafloors. This here would be the amplitude extraction of the same surface. And when we project down the outline of the sills, we see that it's a very strong correlation between the termination of the sills and the presence of these hydrothermal vent complexes. So expulsions of hot fluids from the subsurface at the time of igneous emplacement. Okay, so let's move to the South Atlantic. We've been working in this area for quite some time. We're working extensively in Brazil, both in the Amazon Parnaíba Basin, so with the onshore magmatism, basically the end Triassic camp magmatism, and one of our main study areas for the past 20 years has been the Karoo basin, where we look at the sill intrusions and the extrusives, particularly in Lesotho. And we also been looking at dating this sort of Jurassic event in Argentina. But today we're mainly going to talk about the Paranaetndeca, so the Argentine margin moving up to the Pelotas or the Campos areas. And we're also doing quite a lot of work on the conjugate Namibian part in the Etndeca province, and also moving into Angola. But just first, some work that we've been doing in terms of characterizing organic rich mid-Permian deposits. It's called Irati in Brazil. The White Hill in Peru. It's called White Hill because it's weathered to be white gypsum deposits. It's totally black and very organic rich sediments, and when sills intrude it, you see a lot of pipe structures coming up, particularly in the western part of the Karoo Basin. This is work that's been done by a PhD student, Lucas Bastos, and he spent quite, and with co-authors in Rio, like René and Egberto, and he spent quite a lot of time on dating ash layers, for instance, in this formation at the University of Oslo, and you see then that this Irati White Hill sea was only lasting for about 4 million years in around 277 million years ago, and forming nice source rocks. And we also tried to compile over the years quite a bit of information related to the timing of the Gondwana breakup, because we're very interested in between magmatism in sedimentary basin and mass extinction and global warming. So we looked quite a bit of the end Triassic event and magmatism in the Parnaíba, but also in the Amazon and soil moss basins. Yeah, the Karoo, as I told, and then into the Paranite Deca. What's also quite specific with the South Atlantic is that you have a lot of post-breakup magmatism, especially on the Brazilian margin, going all the way from Campos Sampos up to the equatorial areas. One showed some very nice also reconstructions and opening of the South Atlantic. So south of the Valvis Ridge, we have these very well-defined seaward dipping reflector sequences near the continent-ocean boundary. And you have sort of a zipper-like opening, so perhaps starting around magnetic anomaly 10 time in the Valanginian, and then becoming progressively younger when you move now northwards. So we see here we compile also the type of wells on the Namibian margin where you find volcanic. So you find it in the Kudu field that's been penetrated, also a few places moving towards the Valvis Ridge. Of course, in the Brazilian margin and towards the Pelotas also, they're quite a bit. But on the Argentine margin, there are no SDRs that's ever been drilled and dated and characterized geochemically. So that is one of the motivation for this upcoming, hopefully upcoming drilling leg to try to sample the SDRs here in the south and the central part of the Argentine margin. But basically here, as we are mapping out the SDRs, you form these quite extensive SDR wedges with numerous sequences. And you can also find some outer high that we typically interpret to be the timing of the when the rift axis was being submerged. But we recognize quite a lot of the same sort of seismic facies units as we see in the Northeast Atlantic. So here's just an example of a proposed drilling target for the Argentine continental volcanic margin. So basically, these boreholes will sample the Neogene and the Paleogene, but the main objectives are to have extensive sampling of the Cretaceous sequence, so the post-breakup, and then drilling a few hundred meters into the feather edge of the SDRs. Been really difficult to find good drilling locations in this part of the world because typically the post-breakup sequence is several kilometers thick, which makes it impossible to use the JOIDS resolution drill ship to sample the breakup basalts. If you go into the ocean basins, the water depth is too big, as I think the maximum length of the drill string is about 6 kilometers. But there are these few places where you can drill basically 1.5 kilometers of post-breakup sediments before you enter into the basalt. So they're just within the reach of the JOIDS resolution drill string. So I'll just go through a little bit of the synthesis here in terms of how we look at volcanic rifted margins. This is just a slide I borrowed from my advisor Olav Eldholm, that was pioneering volcanic rifted margin studies and drilling from the 80s. So basically the scientific challenges is really related to how the volcanic margin works. That is, we want to understand the processes, the rifting processes, the melting processes. We look at the initiation. So that is partly what Juan's been presenting. The development of the pre-syn and post-rift, and then the implications. And some of the key premises here is that volcanic rifted margins is a part of a tectonomagmatic system. You need to have a well-established plate tectonic framework. And then afterwards we can look at the global implications for understanding the Earth interior. For instance, the necessary presence of mantle plumes or not, and then also how these large igneous provinces influence the Earth environment. And what we are working extensively on is to see how lips are causing global climate changes and extinctions. It's just a series here of SDR models that have been compiled. You have the typically like the flexural subaerial seafloor spreading. It's initially proposed by Palmason based on Iceland and modified by John Mutter. Then you have more the fault controlled one where the SDRs are formed by infilling of rift basins. And then you can have more of the hybrid type of sort where you have been more recently proposed for the South Atlantic by McDermott and co-workers, where you have rift basins that's being infilled, forming SDRs in the landward side, whereas when you move towards oceanic domain, you will have more subaerial seafloor spreading, and you have the flexure type of SDR setting. Don't think I need to go much into this as it's been presented very well previously, but basically this is the breakup model. So the plate tectonic framework, where you have initially around Valentinian time, you have the early breakup. It's a big challenge to really know how far it went and what is the age of the volcanics along this 1,000-kilometer long margin. And then you had sort of the final breakup and steady state seafloor spreading, sometimes in middle Cretaceous. And then it's really, is it necessary here to have a mantle plume, or was a melt formed by some other type of processes? So this is just a cartoon put together by Roman Meyer et al. So basically, what is the mechanism of excess magmatism? Is it related to a thermal anomaly due to rising hot material from the core mantle boundary or within the mantle? So we get this upwelling of a hot mantle, we get decompression or melting during rifting, and we get this massive large igneous province. Or can we create the magmatism due to some sort of more localized melt generations, for instance, edge-driven convection during breakup, or a fertile mantle? So if we have a lot of volatiles, for instance, in the mantle, we do some rifting, we have lowered the solidus, and we will cross the solidus and produce large volumes of melt during the early stage of rifting, and this will then assist the actual breakup. Just also add, based on the question that I got, some of this the rifting geometries that we have in this the rifting models. So we'll have the classical sort of pure shear model of Mackenzie from 1978. Then it's more like the simple shear model of Wernicke, where you sort of have faults cutting through both the crust and the lithosphere. And then, like in the 80s, Lister would propose a more hybrid models, where you have a simple shear in upper crust and pure shear in the lower crust and the mantle. And then you have various variations of these type of models. you know, in Oslo, they've been we've done a lot of work in terms of more on the crustal part on this margin. This is Dimitri Sastranov that just successfully defended his PhD last year. That's worked a lot in sort of trying to characterize the outer margin, and basically finding that you have a lot of most likely rift blocks below this marginal high. So it's a mix of continental material with magmatic material above and below. And also numerous models produced by our French colleagues, Laurent Grefroy and his students, when they introduce this sort of terminology of L blocks and C blocks and so on, where you basically have this upper crustal detachment faults, and you can have then SDRs formed on both sides of this, like in the Lakshmi Ridge, as an example they've been using in the Indian Ocean, that they can dip both ways. And again, we have this high velocity lower crust in these parks. Just talking to some of my colleagues, Daniel Schmidt et al. Here that works for developing software in geomodeling solutions, and he strongly also emphasizes the importance of sediment blanketing as an important process when you want to understand the temperature history here. So basically, if you take a 1D model here and the evolution of a rift, you can see this is basically time evolution of this point when during the syn-rift and post-rift time. And the main really point here is that you get very different heat flow models. If you're using typically like McKenzie type of stretching models, where you get the increase in heat flow during the syn-rift and then the thermal relaxation, whereas if you have syn-rift sedimentation, you get actually a decreasing heat flow at the base of the crust in the initial syn-rift stage, and then you got a longer term for the relaxation and into the steady state. This is being published in a paper quite recently from Alban and Dani and Lars Rupke. So I'm just going to round off here to look at some of the key aspects of prospective volcanic basins. Clearly, the magmatism will lead to enhanced maturation. So where we have thick extrusive deposits, we get rapid burial that will influence the heat flow history. And around sill intrusions, we will get a thermal aureole. We form a lot of fluid flow and we generate these hydrothermal vent complexes, but sills and dikes can also compartmentalize the basins, and you can have fracture systems along the edges. But perhaps the most important thing is that we get a lot of variety of hydrocarbon reservoir or plays associated with these volcanic deposits. Like in the Nuken, you know, you can produce from the sills, fractured sills. Some places the sills are more permeable and they can work as seals. You will form these sort of typical saucer domes above these sills, and you can have intra-basalt reservoirs like in the Rosebank field in the west of Shetland, and then we have supra-basalt plays basically. So it's a lot of prospectivity around it, but we are still always struggling with getting the perfect images in many of these volcanic margins and basins. So just to finalize here, we are coming back to the Northeast Atlantic to drill a series of boreholes. I'll be the co-chief on this expedition with Christian Berndt, and we go out in August and September this year. And we really want to test end member hypothesis for the formation of excess magmatism and see how lip volcanism is a driver of short-term and long-term global warming. As a follow-up, we've also been involved then in what is called IODP Proposal 1000 at the moment. So it's exploring South Atlantic continental breakup. and transition to passive margin and its impact on Cretaceous Cenozoic climate. Denise Kulank is a lead author on this, and it's a lot of YPF and Argentinian involvement, but we also had some minor contribution to this proposal, and hopefully it will be developed into a drilling leg in the near future. So partly it's two sites that will be drilled, one in the sort of the southern part and one more in the central part. So 3 hole, but 2 of them will hopefully drill the basement. So just my conclusion. So extensive breakup related volcanic complexes are both present in the north and south Atlantic continental margins. The major variations in basalt thickness along the margin, with potentially prospective subbasalt sequences. The deep structure of the outer Argentine margin is poorly constrained, as no scientific or industry boreholes exist. And the scientific will provide new and important information about the volcanic rifted margin formation. So it's the melting processes and mantle plumes, rifting processes and continental breakup. We work on the lava emplacement and magmatic phases, and then the climate environmental implications. So I'm very much looking forward to work on these problems and in these margins over the coming years. Thank you very much.
Thank you, Sverre. An excellent presentation, very interesting. Very complex type of margins, is volcanic ridge margins. So now we're gonna move on to the Q&A session. Please, Sverre, let me know if you need a glass of water. Yeah, I see you.
I have.
That's good. A sip at your glass of water. And Juan, you can
it's always
probably
strange, you know.
Yeah. Strange because you're talking to, you don't see the audience here.
Yes, I'm talking to the screen. I don't know if you.
Yeah, you're right. But we're here. We were 160 something. Now a little bit less. And Juan Pablo, yeah, great that you connected your camera. Okay, so I guess I'll pass the floor to you, Nestor, so that we can start on with the questions answers Q&A session. But let me start with a short one, of just because you just mentioned this interesting project in the South Atlantic about an IODP leg. I've heard something about that, but how soon are we of seeing that materialize? And well, I just heard there's 3 wells. Tell me a little bit more about that project. That sounds really important.
Well, it's moving into its second stage, basically. I think Juan can add quite a bit, because it's been a long process of planning. In the Atlantic, in North Atlantic, it took us almost 15 years, you know, and then suddenly everything happened last summer, and we had to move. So then it moved quickly, and the way they evaluate the proposals is much faster now than it used to be. So since these proposals been through the system before, I think we should know. Well, we'll probably be asked to submit some changes in October, but it's at a fairly mature stage. So within 1 year, we should know if this will be likely put to scheduling or not. And then, of course, we don't know how the world would be, but it either will happen within, let's say, I'm more looking at a 3 to 4 year period, perhaps, and
okay,
or it will never happen.
But this is what you said, Sverre. This is very exciting. We are very excited about the project. Juan Pablo, you, and a lot of people in Denise are working on there. And for us and for Argentina, I think this is a very important project. I'm very happy that you introduced this topic in this chat. Thank you very much.
Yes. It's a very fascinating margin, and with all of the new seismic that you also been getting here over the past decade, it's I think I'm very happy with the borehole sites. I think it's very difficult to find better places to drill than what's been selected, and that is a very good start. That we feel confident that these are good sites and that we have some nice Cretaceous and some nice let's say post breakup and breakup targets. So it will be very exciting if it's going to happen.
Wonderful, wonderful. Okay, Nestor, do you want to
Shot you.
say again? Okay, so we have a list of questions now. The people are actually posing questions, and I have the first one for Juan Pablo. So this is Daniel Minicini asking, is there a smoking gun relating Karoo, Chonaike, lips, and source rocks? You explained the dating of Colorado Malvinas basins. Would you mind to expand on the methods and biases of dating other drifts whose rocks are offshore today? How large are the error bars in those dates?
Excellent. Yes. To address the first question, the Karoo magmatic province was in place in an intracontinental location. So most of the sedimentary systems associated with it are continental, and the challenge there is the climate. No, how was the climate at the time of extrusion, to associate which were the sedimentary environments that were developing, and how rainy was it, as to have a positive budget of rain to grow lakes. We do know that associated with the Chonaike magmatic province, there are lacustrine systems developed both in the early Jurassic, for example, in the Cañadón Asfalto Basin. There's lacustrine systems with proved with rocks, lacustrine rocks that have a potential for source rock, and also in the Austral and Malvinas basins, where there are lacustrine source rocks interbedded with or just below, or interbedded with the Tobifera series in the early and mid Jurassic, and also associated with breakup of the Weddell Sea since the late Jurassic. There's the incursion of marine transgressions, both in the Malvinas, possibly, well, also in the Austral Basin along the Cordillera axis. We know there are marine rocks of late Jurassic age. And with the new data from the Malvinas Plateau of oceanic crust, we know that the late Jurassic Sea flooded the Oteniqua Basin on the African plate, where there are late Jurassic rocks, marine rocks drilled in the west, and the extension of that sea in that what we call the Gonguanid core that was being extended in the late Jurassic remains to be comprehended or continued to study. Obviously, that's that Bermuda's Triangle between the Colorado, Rawson, Oteniqua, where historically there has been very, very little data, and now with the new seismic surveys and the exploration that's going to take place in the southern margin, we will definitely know more about the evolution of that area that was yet so poorly constrained. Regarding the other question, was the errors. The errors is quite a topic. There are, historically, biostratigraphy has been used to date the sequences, and the marine sediments in the offshore wells in these basins that we've been reviewing are clear since the transgression of the latest Cretaceous. Before that, because of the position of the wells in very proximal locations, the sediments or the sequences that have been drilled have been barren for biostratigraphy. Obviously the depot centers themselves are very hardly drilled because they are very deep. So we explore the shoulders of the rifts, and those in those positions, the post rift that has been drilled has been fluvial. In the 60s, in the 80s, and in the 90s, it was hard to date those sediments. Today, we have the technology of the treated zircon dating that will allow us to have much better resolution on the geochronology and the provenance areas for the sequences in the Cretaceous that might be continental. And as we move offshore, we could be finding these sequences in more marine environments. So we could also get data from biostrat. But so far, we have dated what we could, and in my review of the other basins that I did not particularly study, I have used ages from bibliography that are sometimes well constrained, especially onshore, and in the case of offshore, normally less constrained. So the ages comes from the tectonic framework mostly.
Perfect.
Okay, one question for Sverre from Pedro Cres. Do you think the layer that built up the magmatic package of the seaward dipping reflectors has been implicit subaerially, or do you think that it's an amalgamation of lava delta? If you consider subaerial emplacement, how do you explain the subsidence or silting of the seaward dipping reflector? In some case, down to more than 8 kilometers in the margin.
Yeah. So we think that most of the SDRs are subaerial lava flows, and that we have drilling results from basically from the Vøring, from the Northeast Atlantic, several places that you see these sort of red weathering horizons in between the lava flows. So we reasonably in the main, the interpretation is quite well constrained by drilling into the upper kilometer or so of the SDRs. But that is on the feather edge of the SDRs. We then, when we interpret these margins, we find these outer high that we think are formed at submergence of the fissure systems, and then we can find SDRs also seaward of that, and we think we can form SDR-like sequences in deep oceanic environment also.
Thanks.
But mainly they are subaerial, and that's of course a hypothesis we want to test on the Argentinian margin. But our hypothesis is that they're subaerial, and yeah, it's quite puzzling. You need this very large subsidence afterwards, and that might be related to decreasing temperatures in the mantle.
Perfect.
Okay, let me follow up with you, Sverre. There is a question from Victor Ramos. Do you think that trench rollback in the subduction could control rifting in the Southern Atlantic margin?
I think it's more related to really large-scale geodynamic processes. I work quite a lot on the Australian margin, and of course you have breakup of the Western Australian margin in Valentinian at the same time. So something major is going on at this time period, and also along the Western Australian margin. I mean, we find SDRs and strong evidence of breakup magmatism with the same age as in the South Atlantic. So it basically starts at a normally 10 time with uncertainty of the picking But of course, a rollback could be related to some changes also in the mantle dynamics. So these can be related phenomena. But we have an episode here where very strong fragmentation of Gondwana is occurring in the early Cretaceous. And it's not really my field to work on these very large-scale mantle processes. So obviously, I'm speculating a bit here.
Okay, I understand. Yeah, one more question then here, and this is for both of you. It's done for Sverre, but I think it's for both. Could you highlight the main implications of the processes forming volcanic margins for oil and gas exploration? So what would be the implications for oil and gas? You talk about some plays, maybe it's the thermal evolution, and Juan Pablo, you can also probably answer.
Yeah, I can. For us, we look. It's relating to the whole petroleum system. Basically, it can start with the seismic imaging. That the basalts are sometimes difficult to image through, so it's difficult just to map subbasalt basins, and then it obviously influences the temperature history of the basin, and so maturation. It can influence the migration of hydrocarbons. It can influence trap formation, because the mechanical properties, for instance, of volcanics is very different from sediments. So that's something that we see, and also it can also, coming back to what Juan was talking about, it can also influence source rock formation, because if you get a lot of ashes in the ocean, it's a fertilization, and you often get blooms associated with these volcanic periods. So you have evidence of these oceanic anoxic events relating to large igneous provinces. So it can be a positive effect or it can be a negative effect, but it's a part of the geological history you need to understand in terms of assessing the petroleum system. So Juan.
Yes, and to add to that, on the architecture of the margin, we see that these SDRs are very clearly restricted to the area of transition between continental and ocean crust. And this area on the South American margin is quite narrow. This meaning that we have quite an abrupt margin with development of sedimentary sequences or systems throughout the Cretaceous that will be conditioned by this architecture of the basement. Let's say we have a steep and narrow slope that is marked by the precedent SDRs. Also, the way these SDRs were in place in different segments conditions the lateral variability of the margin, and they create, for example, embayments which could favor the development of source rocks, and in the interaction with these hydrothermal fluids definitely could add nutrients to boost the richness of the source rock. This is still a matter of study, but it's obviously there are advantages and disadvantages. These are some of the advantages. Also, it's important, I think, to mention here that the Kudu field in Namibia, there was a discovery in the 80s of a gas in offshore Namibia in continental sediments that are interbedded with basalts that are very closely related to SDRs. They are probably slightly younger than SDRs, but it's an environment where in particularly in Kudu, there was a trap configuration to be able to trap hydrocarbons and it's one of these evidences of active petroleum systems in the southern South Atlantic.
Interesting, definitely. So everything is interrelated. It's no surprise. Yeah, Nestor, you have one there now.
No, I think that for me, it's okay. I don't know if you have something more.
Yeah, I
Sebastian?
have one here. I have one more. It's more on the, do you have any knowledge? This is from Jose Bernaus. Do you have any knowledge of carbonates with good reservoir property deposited on top of as SRDs? Any example with this might have been drilled?
Not on top of the seaward dipping reflectors, no. But of course, on top of seamounts, you will have it. So that is another setting. So it would be in these outer highs, but I mean, if you go if you move toward the Santos Campos, of course, you have sort of SDR sequences, and then you have the post-drift sequence with carbonates, with source rocks and so on in the pre-salt. So I mean, but of course, it's much more difficult to map the volcanic deposits basically north of the Rio Grande Rise Walvis Ridge in the Campos Santos areas of Brazilian margin. That we know that it's quite a bit of breakup related basalts there, and also on the conjugate Angolan margin. But the seismic fasces are not as well displayed as they are on the Argentine margin, where they're very clear on the seismic data.
Yeah, true.
So in that way, Campos Santos or Angolan margin Kwanza Basin, for instance, would be the most relevant type of places where you find carbonates on top of the SDRs.
Yes,
Good.
to add to that, there has been some carbonates drilled in Africa, on the African conjugate, on top of SDRs in Moosehead. So there are development of carbonates. The reservoir quality, I have no information to say, but what I think it's important is that not only carbonate, but also other transgressive plays could be interesting associated with the Aptian source rock, lateral or more proximal equivalent to that, as is the case of our producing Austral basin in southern Argentina, no? Where there's a transgression of the same age and a transgressive system with clastic reservoirs that is successful, produces.
Mm-hmm. Yeah, definitely.
Okay. The last question from Sverre.
Yes. Yeah.
It's from Patricio Marshall. Sverre, assuming the drilling proposal is accepted, how long do you guess will it take for the data to become published after drilling as ODP processing or progress report? And the second, I understood that at this moment, any time to start drilling and release of result is only guessing, but which will be the time frame?
Mm-hmm.
Yeah, so basically, the normal procedures in IODP is that it's a 1 year type of memorandum for the people that go offshore, for the scientific crew. But it's possible to apply for getting access to data before that also. But normally maximum 1 year to post cruise until data becomes public. So it will not be so that is the normal way. And no, I mean, when it comes to timing, it let's say 2 years would be the absolute fastest that I can envision. Then it depends on the ship schedule and what the world looks like in 2, 3, 4 years ahead. But it takes. I mean, if it gets accepted after a year, it's also a lot of sort of safety panels and environmental protection panels and so on that needs to be passed. but yeah, so 2 years will be the absolute fastest, and after that, yeah, it depends on the schedule of the ship and the funding.
We can
Okay,
tell you're an explorationist, Sverre. To me, 2 years is quite fast.
Yes.
No, amazing. That would be great if we can move forward with project like that. That's gonna be really a boost for the knowledge of our margin, and of course also it's gonna have implications for the industry too. Well, I have the last question now for Juan Pablo, and also there's a question here on what event do you associate with the truncated Triassic sediments in the flanks of the Colorado Basin? I also had a question myself on those, because I can see that in first the orientation of those Triassic faults in your map are kind of east-west. So I can see the structural grain that is controlling probably their orientation, but they are also restricted to a small area. Probably, I don't know if you can develop a little bit more on that. There should be a little bit more. What do you think? What's that Triassic there doing?
Our interpretations here of the Triassic deposit centers in the Colorado Basin are directly related to the area where the Ventania fold and thrust belt developed. This has been studied by Pangaro before, also with Victor Ramos, and they established the extension of this fold and thrust belt offshore. What we have seen is that the depositors and the tilted blocks, in this case in the northern flank of the Colorado Basin, coincide with the previous fold and thrust belt. And the fact that the detachment is becoming shallower toward the north of the Colorado Basin makes us think that that's more or less the end of that of the Triassic Basin. Now, it's true there's a lot of exhumation, and if you see those blocks, those tilted blocks, the seam rift associated to them has mostly been completely eroded, so that we only see the pre-rift, the tilted pre-rift there. And the erosion there, I think, is a combination of both erosion on the flank of on the northern flank of the Colorado Basin. So when the eastern deposit of the Colorado Basin was subsiding, the flank was being uplifted and providing sediments towards the deposit. And also because they are quite towards the east, they might have been eroded during the Cretaceous, with being the source of sediments towards the margin, towards the east, towards the Atlantic. Because we know that the Tandilia High, where these blocks are just south of the Tandilia High, we know that the Tandilia High was not completely covered in sediments, or let's say the Tandilia High was a positive feature until the end of the Cretaceous. So all throughout the Cretaceous, the Tandilia High was a positive feature dividing the Colorado from the Salado Basin, and it was let's say created embayments south and north of it, associated to the Salado and Colorado Basins, respectively.
Okay. Thank you very much. Estamos terminando la sección de hoy. Nuevamente queremos agradecer a Juan Pablo y Sverre por su tiempo y calidad de presentación. Thank you very much, Juan Pablo and Sverre, for your time and the high quality presentation shared today with us. Muchas gracias también.
Thank you. Gracias.
Chao.
Muchas gracias. Chao.
Muchas gracias a todos.
Wait.
Gracias a todos los asistentes que se unieron a este evento y participaron con la sección de preguntas y respuestas. Antes de despedirnos, les comentamos que el próximo webinar del ciclo de conferencia 2021 será el jueves 22 de abril, correspondiente al ciclo Magmatismo y Sistemas Petroleros, con el título Multi-Scale Structure Associated with the Igneous Intrusion and Implication for the Fluid Migration, an Integrated Field, Seismic and Modeling Study. Será presentado por Olivier Galland del NGORD Center from the Oslo University, and should be moderated by Ezequiel Lombardo from Chevron. El próximo webinar del ciclo de conferencias de exploración offshore en el Atlántico Sur será el jueves 27 de mayo y tratará sobre los modelos de ruptura continental por Christian Heine de Shell y rocas madres del Atlántico Sur por Johannes Vendeburg, y coautores son autores de Total, Front Total. Sebastián, muchas gracias a todos y por ser parte de este ciclo, y bueno, los esperamos para la próxima.
En la próxima webinar. Muchas gracias, Juan Pablo. Muchas gracias, Sverre. Thank you very much, guys. Amazing. Good session. Thank you.
Muchas gracias por la invitación.
Gracias a todos.